I welcome you all to this 4-week MOOC course, week 1, lecture 2. So in lecture 1, we have seen the frequency response analysis of passive RC low pass filters. Now the another important theorem which will be very much useful in the high frequency analysis of BJT and FET circuits, that is Miller's theorem. So for a simple two-port network, an impedance is connected between two ports. Here, the impedance is connected between input and output. So, using Miller's theorem, we'll replace this impedance towards input side and output side without changing the parameters of the network. So, we'll move that on towards input side and output side. That is the importance of Miller's theorem, and which is very much useful in the analysis of BJT and FET circuits. So that impedance, the feedback impedance, is moved forward to input side and output side, denoted here Z1 and Z2. So we'll derive here, but the formula is given here. It is Z1 is equal to Z dash by 1 minus K. Z2 is equal to Z dash into K by K minus 1. K is actually the gain of the system. Here V2 by V1, that is the voltage gain of the system. From the first diagram, I1 is equal to V1 minus V2 by Z dash. So I1 is equal to V1 minus V2 by Z dash. From that, we can do a simple mathematical manipulation here, taking common V1 from the numerator, which leaves 1 minus V2 by V1. V2 by V1 is K. So making it as I1 is equal to V1 into 1 minus K by Z dash. And further, I1 is equal to V1 by Z dash by 1 minus K. So V1 by I1 is the Z1. So Z1 will become Z dash by 1 minus K. So from the second diagram, we can write I1 is equal to V1 by Z1. Comparing the equation 1 and 2 leads to Z1 is equal to Z dash by 1 minus K. Similarly, from the first diagram, we can write I2 is equal to V2 minus V1 by Z dash. So taking common V2 from the numerator, 1 minus V1 by V2 by Z dash. V2 by V1 is K. So V1 by V2 will become 1 by K. So making substitution, I2 is equal to V2 into 1 by 1 minus 1 by K by Z dash. Making it more simpler, I2 is equal to V2 by Z2, and equating 3 and 4 gives Z2 is equal to Z dash into K by K minus 1. So formula that for Z1 and Z2, the feedback impedance is replaced and forwarded, the moved from both input side and output side. And it equivalent values. Z1 is equal to Z dash by 1 minus K, and Z2 is equal to Z dash into K by K minus 1. And if the feedback impedance is a capacitance, because in BJT and FET circuits, feedback capacitance will be there. So we should know this factor. If feedback impedance is capacitance, C dash is connected between both input and output. So we're making substitutions in the previous equations. That is, Z dash is equal to 1 by j omega C dash. Z1 is equal to 1 by j omega C1. Z2 is equal to 1 by j omega C2. Substituting the above terms in the equation 5 and 6 gives Z1 is equal to Z dash by 1 minus K. So we are substituting 1 by j omega C dash and 1 by j omega C1 in this equation. 1 by j omega C1 is equal to 1 by j omega C dash is equal to by 1 minus K, which can be written as 1 by j omega c dash into 1 minus k. Comparing these two gives C1 is equal to c dash into 1 minus k. This is the parameter which is useful. Similarly, in Z2 equation, substitute Z2 is equal to z dash into k by k minus 1. So substituting 1 by j omega c2 in Z2, z dash plus 1 by j omega c dash, and making the substitutions and simplification, C2 is equal to C dash into K minus 1 by K. This analysis is very much useful in high frequency model of BJT and FET for simplification. In specifically high frequency analysis, capacitor will be there in both BJT and FET circuits as the feedback element. So these two parameters, C1 is equal to C dash into 1 minus K, C2 is equal to C dash into K minus 1 by K, which is useful. K is equal to V2 by V1, the voltage gain of the circuit. This is the Miller's theorem. Next. In general, analysis of amplifier which improves the gain of the input signal, increases the signal strength. But the analysis, small signal analysis and large signal analysis. We'll discuss large signal analysis as a power amplifiers, small signal analysis as a voltage and current amplifiers. Again, it is divided into two parts, DC analysis and AC analysis. DC analysis to find the operating point. We have seen this in electronic devices circuits. The transistor should be operated in active region, that is the BJT should be operated in active region to amplify the input signal. So we'll see in which region the transistor is operating. So while performing the DC analysis, AC sources will be replaced with its internal resistors. Capacitors will be act as an open circuit because capacitors for DC means F is equal to 0, 1 by j omega c. F is equal to 0, it substitute infinity. So it is open circuit. While performing AC analysis is to find the various gains, input impedance and output impedance, for which DC supply should be connected to ground. DC supply will be connected to ground. This is both DC analysis and AC analysis. And next one is low frequency. AC analysis is again divided into three parts: low frequency analysis, middle frequency analysis, and high frequency analysis. While discussing electronic devices circuits, we have already gone through the H parameter analysis, which is sufficient for low and mid frequency analysis only. High frequency analysis, H parameter is not suitable. So, hybrid pi model, the name pi is given because the circuit looks like a pi. So, hybrid pi model is the exact electrical equivalent circuit of BJT. But we can say that by making high frequency substitution and making it assumptions, it is equivalent to H parameter model under low and middle frequency analysis. It will be equal. So that's why we discussed in EDC H parameter, which is sufficient enough to discuss it in low and middle frequency analysis. So DC analysis, just now we have seen DC analysis is to find the operating point of the transistor, and a self-biased circuit is the most important circuit which provide stable operating point irrespective of variations in temperature and aging effect. The circuit you can see here, R1, R2 is a potential divider network, RC, VCE and RE. Operating point is always VCE, comma IC. This is replaced with its equivalent circuit. This analysis is there. VB is equal to VCC into R2 by R1 plus R2. RB is equal to R1 into R2 by R1 plus R2. See, in general, thermal runaway temperature increases ICVO, the reverse saturation current, which doubles for every 10 degrees raise in temperature, which in turn increases collector current. Collector current IC will be increased. So IC means power across the collector junction. PC is equal to VCE into IC. IC increases power dissipation across junction increases, which increases the temperature at the neighborhood of the junction. Temperature increases again the ICBO. It is a cumulative action leads to thermal destruction of the transistor. But see here, in this circuit, RE is providing thermal stability. How? Verified, mentioned here. Temperature increases. Temperature is increased. ICBO increased. ICBO increased. IC increased. IE is also increased. IE is equal to IB plus IC. So IC increased. IE increases. IE increases. Voltage across the emitter resistor increases. VE, the voltage across emitter resistor increases, which decreases base to emitter voltage. VBE is equal to VB minus VE. VE increased, VBE decreases. When voltage across the base emitter junction decreases, the base current decreases. Base current decreases. Base and collector current are related by IC is equal to beta into IB. That is IC decreased. Here because of temperature IC increased, but here we are using emitter resistor which is reducing the IC. So which stabilizes the operating point of the transistor. RE is the important factor in operating point calculation, which is stabilizing the operating point of the transistor. That is irrespective of variations in temperature and aging effect. Then I want to show some important discussion regarding small signal AC analysis. So it is H parameter analysis. You can see V1 is equal to H11 I1 plus H12 V2. I2 is equal to H21 I1 plus H22 V2. A simple point here I want to mention here is that from the characteristics of the transistor, because its behavior, that is input voltage and output current are function of input current and output voltage. That's why H parameter analysis is utilized. And we can say H11 is HI, H12 is HR, H21 is HF, H22 is H0. So this is the diagram. For SCE amplifier, the equations are IB, VBE, IC and VCE. AI is equal to minus HFE by 1 plus HOE ZL. Because this is very much useful while calculating the gains of the circuits I have mentioned here. Then input impedance Zn is equal to HIE minus HFE HRE ZL by 1 plus HOE into ZL. This is actual formula. Making substitution again, AI gives this answer. And always voltage gain is equal to current gain multiplied by load impedance divided by input impedance. Similarly, Y naught, generally output admittance. Y naught is called output admittance. Y naught is equal to HOE minus HFE HRE by RS plus HIE. AVS and AIS is means with considering the source resistance of voltage source and current source. So AVS is equal to AV into Zin by RS plus Zin. AIS is equal to AI into ZL by RS plus Zin. This analysis is very much useful finding the gains and input impedance of the BJT circuit. So this is a small signal H parameter equivalency here. Because we are doing AC analysis, this is the circuit where all DC sources are connected to ground. RS, VS connected to ground. Capacitor is replaced here because I'm doing the analysis of mid frequency. So R1 connected to ground, R2 connected to ground, transistor, RC connected to ground, RE and CE. And we will discuss this actually, CE, which will not disturb the operating point of the transistor, but provides what I can say, CE bypasses the negative feedback effect to the transistor. These are the gain calculation we'll see with RE without CE. the calculation. Without RE, with the C, this is the gain calculation. These things will be discussed again in detail in the feedback amplifiers. So that's all for the second session. The mostly concentrated on Miller's theorem and some basics of BJT circuits. So thank you.